So this is code basically where sorry, I'll just adjust the screen. So this is basically code where you have a producer that produces a sequence of integers. So it basically produces 1, 2, 3, 4, 5 until some limit, and the consumer that consumes this number and prints the number. So it's a very simple program which basically sort of iterates from one to a limit to some number, and then uh, and then basically prints out the output from the program in steps, right? So in this program, you have the put and get that we looked at, and then you have a producer that takes as input the limit, the maximum number that you're going to print, or actually the number, like the, yeah, you'll print that number minus one, basically. So it takes arguments, and this is basically converted then to an integer, which is arg, int arg, and you store it in a variable that's called loops. You have int I, which is an iterator basically, and for I is equal to 0, I is less than loops, so you basically iterate from 0 until the loops minus 1, and then I plus plus, and then you put I, you call the put function that we called. If basically count is equal to 1, then you will have to wait. If count is equal to 0, then you can basically store the value into the buffer. The consumer, on the other hand, will basically again take args as an input. Okay, you have an iterator, and while basically you're for infinity, basically you're going to consume this data. So you're going to get the data and you're going to print it. Here, the args that are passed to consumer are actually not really necessary. You can actually do without that, but I mean, for a more general program, this might be needed. Uh, so this is actually a solution, because if the previous code had absolutely no guarantees and no locks, no anything that guarantees synchronization. So this is one solution that can slash might work, that you might think of by basically using locks and conditional variables, where the producer basically before basically acquiring before changing before acquiring the buffer, before trying to add something to the buffer, it calls a lock. It basically checks if count is equal to 1. This is basically instead of asserting. So if count is equals to 1, you're going to wait until count is equal to 0. When the consumer runs, basically it sets count to 0 once it's done. So it's basically you're using the conditional variable to make sure that the counter is either 1 or 0 when you're in one of these two threads. So let's go through the producer code first. So you have int I for I is equal to 0, I is less than loops. I mean, the loops definition here is missing, but you get the idea. You basically, it's also a mistake in the book. You should have basically the initialization of loops just like here, where you had loops as an integer of arg. Okay, so you basically go through, iterate through from I equal to 0 to I equal to loops, I plus plus. You call your lock, you acquire a lock basically. Of course, you have defined the lock before. And if count is equal to 1, which basically means that, well, there is someone now using there's some data now that has been produced before that is stored into your buffer, because count is basically the number that you're using for the number of items in the buffer, right? So if count is equal to 1, that means there's data, so you are going to wait on a condition, and that condition basically is count should be 0. Okay, if count is not equal to 1, you're going to put I into the buffer, and you're going to basically raise the signal, basically the condition for the condition um, that you already have put data into the buffer, so any consumer can now read that data, can pull that data out, can get that data, and then you unlock your lock. Okay, then your consumer code is basically, yeah, it's exactly like it has exactly the same logic. You're basically trying to make sure that when you try to pull data from the buffer, there is actually data in the buffer. So you basically start by doing the loop, and if count is equal to 0, okay, of course I mean, here for I equal to 0, I is less than loops is actually unnecessary. You could have it as while 1, basically. So this is basically just an example. So you can have while 1. You basically try to lock the lock first, so that you make sure that the buffer, this is a lock basically for the buffer, right? So if the producer is now trying to put data into the buffer, the producer has the lock, you cannot acquire the lock. If the producer does not have the lock, that means that the producer is not using the buffer right now, and no other consumers are using the buffer right now, so you can actually use the buffer. So you lock the buffer, you check if count is equal to 0. If this is the case, then you basically have to wait. Okay, this is a broken solution, by the way. We're just going through it, but it's a broken solution, as the title says, and we'll see why. And then you wait basically for the condition, and once the condition occurs, basically count is equal to 1. Now count becomes 1 because the producer has produced some data. You can get the data, you can then basically signal that you have emptied the buffer, and you unlock your lock, and then you do whatever you want to do with that data. So how would this work if you have two consumers? And this is why this is a broken uh, solution. So in the beginning, you have TC1 thread. If you look at the different fields here in this table, you have TC1, which is basically thread consumer 1 state, TC2 thread consumer 2 state, TP thread producer state, okay, and you have the count, and you have comments basically that we add. So as you see, you're starting basically, I mean, we suppose that the scheduler starts from this thread line. You're basically that your TC1 is running, your first thread is running, your first consumer, the right hand consumer is running, and basically it tries to call to get access to the lock. So it's running, everything else is ready, okay. And if count is equal to 0, again in that case, so you moved one step, and you see that TC1 is still the one that is running, okay, and while the other two are in ready state, okay. If count equal to 0, it is actually equal to 0 because nothing is produced. So C1 goes to sleep, and now there's nothing to get, okay. And you have basically two other threads that can run, okay, TC2 and TP. Now the first thread, the first consumer, is waiting on the conditional variable to occur, right? So this producer now starts running, tries to acquire the lock. It can acquire the lock, right? Can it? Yes, it can, because the other thread, when it went to sleep, it basically released the lock. So it was able to acquire the lock. It's still running, and TC2 is in the ready state. Okay, so if count equals to 1, is count equal to 1? No, it's not. So you're going to put some data in here. You're going to put the value of 1. So you have basically count now has 1. And if you're starting basically from I equal to 0, then you're putting 0 into the buffer. Okay, so now this is running, this is ready, and this is sleeping. Okay, so Now you're still running, but when you basically signal that the condition has already happened, basically count is equal to 1, you can consume the data now. Okay, you will basically have both TC1 and TC2 now in the ready state, because the one that was sleeping can now wake up. And again, you release the lock because you had the lock, and you basically can stop running, right? Now you have uh, you can have that the producer thread run once more. Maybe it's round robin, and you still, your time quanta has not was not completely utilized, so you're still running in the producer, uh, with the producer basically being the one that is running. The producer tries to acquire the lock again, so it acquires the lock again. If count is equal to 1, yes, count is equal to 1. So now you go into that if statement, and the producer goes to sleep, the buffer is full. Okay, now while the producer is sleeping, one other thread can get scheduled, and now it's TC2's turn, because it's, well, going in turns. So it starts running, basically acquiring the lock. Okay, and now if count equal to 0, it's not equal to 0, so it gets grabs the data. Okay, and now pthread conditional signal, so it's now going to basically uh, since it grabbed the data, it basically, and TP was sleeping, right? Because that's the was sleeping before. Now when the signal is sent, TP will wake up, so it will go from sleep to ready. Okay, and then it releases the lock. Okay, and then you have C4 now. Okay, C4 was waiting, if you remember, right? It was checking if count equal to 0, right? And count now is equal to 0. So although the condition basically was signaled to have passed, then what happened here is that since you had the same conditional variable working for both the consumer, the producer, and the consumer, you had multiple consumers. What happened is that the second consumer grabbed the data that the first consumer was waiting for. Okay? And now, when the first consumer woke up, it has no way to double check. I mean, it cannot basically run the code backwards, right? It cannot check if count equal to 0 again, right? So it has already been waken up. So right now you have an issue. I mean, you're trying to get data that is non-existent. So signaling a thread only wakes them up, but it does not guarantee that when they run, the state will be as desired. This is actually something that is called, it's studied in real-time systems and hybrid systems theory, and on basically model proofing and model checking. It's more related to theoretical computer science, and it's called the mesa semantics. There are other ways to implement this using something that's called the Hawari semantics. Hawari actually got a Turing Award for his ideas. It has much stronger guarantees for conditional variables, basically, but it's very complicated to implement. Therefore, most systems use the mesa semantics, which are actually broken, as you have seen.